All right. Hello, everyone, or possibly just Alex. That's fine if it is just Alex, because Alex is the one that asked this question. This stream is about geometric algebra programming. In this stream, we are making a virtual reality animation program. We're making it slowly. We're making it with lots and lots of clever maths. The clever maths that we're using is geometric algebra. It's much simpler, much more beautiful, much more visual as an approach to doing game engine development and CAD software development and even physics, this kind of thing. This first couple of streams is going to be just clarifying lots and lots of stuff around geometric algebra, and then eventually we'll spend more of our time on actual programming. And in particular, this stream is going to be about how in the thing that is known as projective geometric algebra, there are different schools of thought about the best way of doing it. There is, let's see, there's the John Selig way of doing it, you might say, and the Eric Lengyel way of doing it. I'm just calling it that because those are the first two people to use these respective forms of projective geometric algebra. Right here on this whiteboard, I've got a picture of the major players in the development of projective geometric algebra. These are Stephen, Leo, Charles, and Eric. I'm doing alphabetical order of their surnames here, and this is John. And Stephen de Kennick, Leo Dorst, Charles Gunn, Eric Lengyel, John Selig. That's not in any kind of chronological order whatsoever. So let's talk a little bit about the chronology of this, though. The start of projective geometric algebra is the year 2000. Going to go all the way up to 2023. Here was where John Selig first wrote about projective geometric algebra. Let's get some basic things here as well. So Charles Gunn got interested, let's call that 2005. Selig paper. Gunn 2005 he started trying to do geometric algebra for Euclidean geometry, and he came across John Selig's work. So that was when Charles Gunn first got interested in it, and then 2011 is Gunn's thesis. And around about the same time, in 2011, completely independently, Eric started working on projective geometric algebra and developed his formulation. And he started writing about that and talking about it, especially at the Game Developer Conference, around about this period of time. I don't know when he first started, but it was just after Gunn. Like I say, independently, but by around another important date. By 2015, Lengyel had done his most important publications on it. Well, his public talks on it, and then I think around 2000. So I think it's 2016. You have. Can we see that properly? Yes, that should be okay. In 2016, you have Ganja.js, which was made by Stephen based on the work of Charles. And then you have sort of competition throughout this period. It's not really short. It would be a somewhat difficult time to get into projective geometric algebra because Well, gun stuff is out there, but it's out there in a somewhat difficult to digest form. Eric's stuff is out there, but Eric's stuff is, it isn't directly compatible. It uses a different notation from the Gunn and Selig and Decenic situation, and so you kind of have to choose one during that period. What's happened quite recently is that Eric's now getting into conformal geometric algebra. Charles Gunn is a fan of conformal geometric algebra as well. And I don't want to call it too early, but there's a potential for kind of converging around conformal geometric algebra as a kind of underpinning of the whole thing. I won't say too much about that because I want to talk about conformal geometric algebra in coming streams. But it's its own complicated thing, and both Gunn and Lengyel were doing their stuff without conformal geometric algebra. So you should be there's a core of projective geometric algebra that's certainly understandable without conformal geometric algebra. But okay, so don't want to do that. Let's go a bit up here and let's talk about what do I mean by projective geometric algebra, because it's very worth clarifying that. And I talked about this a lot on the previous stream, but I'm just going to summarize what I said in the previous stream. So you've got projective geometric algebra. It's like this, and within projective geometric algebra, you have Euclidean projective geometric algebra. Oh, that doesn't quite fit. Pity. All right. And Euclidean projective geometric algebra lets you do lots of nice things. Let's list those. Points, lines, and planes, new line. Rotations and translations, new line. Projecting things onto other things, new line. Measuring angles, new line. Intersecting objects, new line. Orthogonal objects, new line. That'll do. And that is what you can do in Euclidean projective geometric algebra. But you also want to be able to measure distances, new line. Take joins, new line. And that's about it for the things that's outside of there. Euclidean projective geometric algebra you can think of as completely... Let's zoom out. This is... We're thinking about the mathematics is fundamentally CL 3, 0, 1. And it has planes, lines, points, rotations. And you can compose rotations and translations using the you've got the geometric product, new line, the wedge product, new line, the inner product. A, B, a wedge B, and the inner product is A dot B. All right, and you want to be able to do all of these things. And last week we only saw stuff that could be in there, and I just wrote it out for you. Okay, and that can be done completely with just this thing CL 3, 0, 1. But you want to be able to do all of these, and John Selig's original paper from the year 2000 was able to do, it gave you a way of doing all of this stuff. That's why we say that John Selig started projective geometric algebra. But what happened after that is that Charles Gunn and Eric Lengyel both, after working with this for some time, decided that they needed a bit more of a... They wanted to think of this as one full system. Full system? They wanted to think of it... They wanted to be able to make the whole thing a bit less hacky. Because here's what happened. John Selig, in order to do the whole of this, he used something called the Hodge dual to get outside of here. That's where I'm going with this. This, on its own, does not have this thing that's very important called duality. And so you've kind of got to introduce it from the outside to some extent. It's the inner product and the wedge product. So the wedge product, which looks like this, A wedge B, A dot B. That's the wedge product. That's the wedge product. Inner product. Not in a product, but inner product. There. This one does intersecting objects, and this one does lots of other. Well, it's part of how you get projections and measure angles and that kind of thing. But there's another product that he introduced there called the join. It looks like this. This is the most general term for it. The most general term for it is the regressive product. Yeah, like that. And this is used. So the wedge product lets you do things like if you've got a line and a plane, you can get the point of their intersection. The regressive product is like if I've got a point and a line, then I can get the plane that contains the both of them. Or if I've got a point and a point, then I can get the line that joins them both together. Oh, apparently my text is hidden. Okay, I need to be a bit more on top of that. So, that's the... Do you know what? I should have done this in red, because the baby blue is working for us as kind of telling us that we're inside of just that part, and then the red is the larger thing. All right. So the duality. This is a really interesting concept. It's a very deep concept. Can you guys see that? Yeah, you can. Duality allows you to associate I'm going to do some other colors. So let's say if you were in 2 dimensions, then duality might let you associate each line to some point, and each point to some specific line. I've made, for the purposes of this stream, a fun way of showing you what I mean by this. Let's just skip to it. Okay. I'm being a little bit hand-wavy right now. I've said a lot about Selig's approach. Oh, and I also haven't said that what happened was that Stephen Deckennick, even though he started out, even though he was I was about to say a student of Charles Gunn. Maybe I shouldn't say that, but he learned geometric algebra from Charles Gunn and from Charles Gunn's work. Stephen Deckennick ended up far more like John Selig. Stephen's got his own stuff going on, certainly right now. But a lot of the stuff that Charles did, especially what I'm about to say about reading into the duality stuff a lot, as in what made Charles Gunn more like Eric Lengyel, Stephen eventually said, oh, not so interested in this stuff. At least he's not interested in it. He doesn't see it as a very fundamental part. Yeah, he doesn't see it as in any way a fundamental part of projective geometric algebra. And because Stephen was the developer of Ganja.js, Stephen and Eric were the kind of main people. If you read something about or watched something on YouTube about geometric algebra for a while, it would either be coming from him, from Stephen, or from Eric. But the kind of the connection via Selig and Gunn was sort of lost, which meant that anyway, so let me show you what I mean by duality. So Stephen has Stephen has the Hodge. All right, let me show you what I mean. All right, I've got a little game here. All right, so this is Polar Tetris, and you can play this game yourself. You can go to the following webpage. I'll put it in the chat. todd1.github.io/ga/Polar Tetris. Yeah, that should be the link that you need. All right, this is Polar Tetris. What the heck is good? What the heck are we looking at here? So it's Tetris. So you can see ordinary Tetris happening up here. I can rotate my blocks. I can pull them down. What's happening here is that for every Tetris block that I've got, the Tetris blocks are of course made out of squares. You can kind of think of each square as a point. What you're seeing behind the Tetris, behind the ordinary Tetris, this bunch of red lines and some lines in the background, you can see that there's a color correspondence between this moving block that's going down here and this bunch of lines that are coming down here. And you might notice that for every Tetris block, of course, there are 4 little squares, and for every bunch of moving lines coming down here, we've got 4 lines. And so what I'm doing in order to make this weird view that we've got behind us is that I'm dualizing this Tetris game. I'm saying for every block in this Tetris game, there's a line in this Tetris, in this strange kind of Tetris. Well, you can't really call it Tetris, can you? This is taking place. Tetris, practically all games, Tetris takes place in Euclidean space. Euclidean space is a place where you can rotate. You can do lots and lots of rotations. You can rotate anywhere you like. And you can also move. And you can move in a way that looks like an ordinary movement. There's no it's not like you move and you inflate and deflate, or you move and your head gets bigger than your feet for some reason. It's not like that. No, you can just take an object and you can move it, and the shape of that object does not change at all. And that sounds like a really boring thing to point out about movement. But the thing is that if we're talking about serious geometry, you tend to find that mathematicians talking about movement as such, they go to very, very, very strange places sometimes. Let's go back to the whiteboard for a bit, and I'll tell you a little bit about that. Probably most people here are interested in applied mathematics, so I'll say that some examples of things that you want to do with applied mathematics include special relativity and electromagnetism, new line, quantum computing, new line, machine learning, new line, continuum mechanics, new line, classical mechanics, new line. That'll do. Oh, 3D game engine development, new line. Yeah, I'll just have that as an extra one. As somebody in the chat points out, because obviously most people are here because they're interested in this one. So you might say, by the way, that 3D game engine development was kind of a From the point of view of a physicist, 3D game engine development is to a large extent it's a lot of it is an application of classical mechanics. Don't want to go too much into that, but certainly classical mechanics is yeah, as somebody in the chat says as well. Yeah, so you got this is you don't have to know anything about all of this crap in order to appreciate this stream. I just want to point out that there are lots of different kinds of geometry that turn out to be useful in these different areas. So to say what's important about these ones first, we tend to say that Euclidean geometry is very useful for that. Hyperbolic geometry is very useful for that. Elliptic geometry, very useful for this one, and I think this one as well. Continuum mechanics, well, I don't know, maybe that's a little bit of this and a little bit of this. I don't know very much about it though. But yeah, there you go. So these are all different kinds of geometry, and again, I don't want to go too much into them because the really important one, especially, so certainly if you're a game engine developer, then this one is wildly more important than these two. But what's happened is that mathematicians, they went to strange places and they ended up finding things that have turned out to be profoundly useful by spending a while being untethered from things that are useful. There's a few video games out there that take place in these rather strange spaces. So, like I say, this this polar Tetris thing that I've made there, that is, so far as I know, it's the first game to take place in polar space, and I don't recommend anybody make any other games taking place in polar space. It seems it's absolutely horrible playing that game, as you will find if you try and play it yourself. But you might have heard of what was it? Okay, so there's Hyperrogue, Hyperrogue, new line. Hyperbolica, new line. There is another game made by a friend of mine that takes place in elliptic space, and it's like asteroids, but on the surface of a sphere. I'll bring that up next time for his benefit. But so you can have games taking place in elliptic space. So you probably ordinary old like Pac-Man, right? Takes place in toroidal space, which, well, basically Euclidean space, but it sort of turned into a toroid by making it so that you come out of here and then you come back on this side. If you go up there, then you come out on that side. And if you go out there, then you come out on that side. So that's toroidal space. It takes place on the surface of a donut, we tend to say. But it's a donut. We say that it's a donut with what's called a Euclidean metric. I won't go into details on what I mean by that, but distances in this in Pac-Man work the same sort of way. If you measure the distance between here and here, then it'll work just like taking a distance between 2 points in Euclidean space. Elliptic geometry was known to the ancient Greeks, and you can quite simply say it's the 2D elliptic geometry is geometry where you're kind of stuck on the surface of a sphere. So you can, for example, measure angles on the surface of a sphere, and you can find slightly strange things like the fact that you can have a triangle whose angles are all right angles, or in general, if you draw a triangle on the surface of a sphere, then the triangle's angles won't add up to 180 degrees, which is what you're taught in school. You're taught in school that the angles of a triangle add up to 180 degrees, but that's actually only true in Euclidean geometry. Angles add up to 180, and here in hyperbolic geometry, the angles of a triangle add up to less than 180 degrees. In polar space, angles work differently. I don't even, whatever. So this is a bunch of geometry, and it's turned out to be useful in applied mathematics, but you'll only hear about it, you tend not to hear about it in engineering courses. Right. But so the kind of pivotal moment for Euclid for these different geometry as a field was I'm not going to try and get the date right, but there was an important guy called Felix Klein. He had something called the Erlangen program, and he kind of announced the idea that we should base pure maths on the idea of kind of having objects and thinking about how objects thinking about transformations that leave objects unchanged. Won't say too more about that because it'll get very abstract, but that was a very, very influential development in mathematics, and as a starting ground for that, he said, so we've discovered that there's not just Euclidean geometry, there's these other kinds of geometry, and they're very important, and he mentioned elliptic geometry and hyperbolic geometry. And he actually also mentioned polar space, or it actually goes under the name dual Euclidean space, but some people call it polar space. And polar space, again, is this thing, you have this space where, I mean, one way of saying it, especially in terms of the description I just gave, is that angles and distances are swapped around. So a distance is usually a thing that you can measure between two parallel lines, where these lines don't meet anywhere, except where that defines parallel lines. Although you could say that these two parallel lines would meet if you went up to infinity, or if you looked at a perspective drawing. Projective geometry has this idea of projective duality, and projective duality is what we're seeing going on in this weird Tetris game. Oh gosh, I wasn't showing you my whiteboard for a bit. That's what I just wrote on my whiteboard. Terribly sorry about that, folks. So there's the picture that I just drew. There's some lines meeting at a point at infinity. This is the line at infinity here. These two are points at infinity. And these are parallel lines, right? Okay. Polar space, like I say, is very, very strange. But there's there's mathematicians out there studying it. I found it kind of useful for thinking about camera transformations, which are of course pretty important in Euclidean geometry and game development. The camera transformations are important. These objects, as they move downwards, like that. As they move downwards, their sort of lines get squeezed together, and that actually happens with a 4x4 matrix camera transformation. In the film industry, they have this term Zolly. I'm going to get rid of that for a bit. I think think we've got what we need from polar tetris. A thing that you might remember if you remember Lord of the Rings, the Fellowship of the Ring, super well, is that there's this part in it where you're kind of looking down this path, and the path seems to you've got trees around it. You've got trees, and somehow the things seem to come towards you, even though the camera doesn't seem to be moving. It's very strange. They call another word for that is the Jaws effect. Another word, the general term for this is a dolly zoom, and then sometimes that gets called a zolly. And I've tried to get people to use this term for a transformation in this kind of polar space. Sorry, no, not I didn't mean to write that arrow at all. A transformation in polar space where that's what you see when you've got a Tetris block moving down in polar Tetris. You don't tend to think about this too much as a game programmer. You kind of make your camera projection matrix once, and then you never touch it again. Maybe you have to think about it a little bit if you are in some strange situation, like maybe you're making a CAD program and you've got a 3D model and you've got kind of two views on it, and you've maybe got one orthographic view and you've got one perspective view, and you're trying to do something, you're trying to have a general interface that works across both of those, and you need to think about like the camera ray and the mouse ray in this window over here, and the mouse ray in that window over there. Can get very, very complicated. That kind of situation, I've not had to do much CAD programming. Maybe that will change now I'm making an animation program, but personally I feel better prepared for it, having spent some time thinking about these Zolly transformations. But, you might not care about that at all, and that's fair enough. And I should have clarified earlier on in this, like, this presentation is very much optional. Like, you don't have to understand disagreements in projective geometric algebra to have a vague idea of what's going on in projective geometric algebra, and that's why I say that you can kind of focus on this one, and honestly, this arrow comes up very little. The main, I've been spending such a long time talking about it so far because, this arrow that allows you to go from, polar projective geometric algebra, and let's draw this again. Hope you guys can see that. Yeah, you more or less can. Polar projective geometric algebra is contained inside there, and I've not exactly connected it up to these things because it's not. I don't even know exactly how it would connect to them. But I'm just saying that polar projective geometric algebra is, which I can maybe color code it a little bit differently. Polar projective geometric algebra is, it's got that going on inside of it. Call it purple. So yeah, there is no arrow there. It's more that these things. It's more that these things make use of this arrow. Yeah. So, one example of a person who doesn't care about polar projective geometric algebra much at all is John Selig. When he was making this stuff, he was just like, You know what? Hodge dual. I don't care about that. Let me say a bit about what the Hodge dual is. Dual. Thank you. Projective dual is this thing that goes between Euclidean Euclidean. Let me just switch to this. Okay, Euclidean and polar does this. The Hodge dual is in a sense, and the point of this is that both of these different ways, both of these mathematically quite well understood things. Like, you can go on Wikipedia and read loads about these things and how mathematicians have used them in all sorts of places. Both well understood things. They both function perfectly well in terms of giving you this arrow over here that you need in order to take distances and take joins. I didn't want to have a little new there. By the way, joins is the finding the plane that contains a line and a point thing, or finding the line that contains 2 points. Right, polar and Euclidean is the projective one, and if you are not familiar with polar space, which practically nobody is, then the projective dual can be quite difficult to try to wrap your head around. A lot of even very, very experienced people, they kind of missed the polar space connection, and they didn't particularly feel like reading about it, and so when they read Charles Gunn's work, they didn't really get that he was talking about two different spaces. A lot of people didn't get that polar Euclidean connection, so they had difficulty understanding, especially chapter 10 of Charles Gunn's PhD thesis. But he did have a visualization of polar space in there. A dual Euclidean the projective dual of a Euclidean translation he had a picture of. And same with Eric Lengyel. So Eric wrote a paper called Space Anti-Space Transformations, in which he talks about polar space, and speculates it could be useful for camera projections. He kind of turned his back on that a little bit at GDC this year. But the polar space is a useful thing in terms of understanding why both himself and Charles they view the dual as something that takes you to a different kind of object, in a sense. Well, beg your pardon. Do you know what? That's a description of Charles. That's not really a description of Eric, and I will get to Eric shortly, but to that difference shortly, and you'll see why Eric wanted to have a different bunch of notation, which Charles didn't. The notation, in a way, you could argue, you could very well argue, makes the fact that you're it does. The Eric's notation makes you feel like you're doing this kind of thing sometimes and that kind of thing other times. But I should say about the Hodge dual, and I should have brought it up earlier actually. So the Hodge dual is here's the way that I think about the Hodge dual. It is simple. So here we go. You've got some things. All right, and you can if you start out making a system by saying I've got those things, for example, they could be E1, E2, E3, then your Hodge dual has the ability to your Hodge dual packages those things together, right? And it allows you to say, for any thing that you might have, no, don't want that color. Gray. It'll give you the things that are in there that were not in the thing that you put in. This is Hodge dualization. Yeah. Nope. That is the Hodge dual. So, if you've got, I'm talking, that's a very abstract picture. Like, what do these squares correspond to? Well, they correspond to nothing in the context of projective geometric algebra. Projective geometric algebra does not contain squares as such. You can make squares out of other things if you like, but it doesn't contain them as a primitive object in any way. I'm just saying here, this is the this is a thing that you can do in projective geometric. Well, the Hodge dual lets you do this in the context of projective geometric algebra. So, to give an example, let's say that I was doing 2D projective geometric algebra. I would have E1, E2, E0, and if I said E1 looks like that, and E2 looks like that, and then I'd have to be saying that E1, 2 looks like that. If I were to say, hey, what's the Hodge dual of E1, 2? Right? What's the Hodge dual of E1, 2? Well, my basis for 2D projective geometric algebra is the thing E0, 2. Sorry. Well, that's the basis. This gets called the pseudoscalar, but that's not a term that I use very much. So this is it's an object that's inside of 2D projective geometric algebra. An example of a place where you might see this object, where you might use this object, would be if you happen to have a glide reflection. So if you were making like wallpaper patterns, and you had you wanted to make you wanted to make wallpaper patterns using arbitrary like reflect and translate, but you wanted to gauge that amount. You wanted to change that amount of reflect and translation. So you wanted to change it between 1 centimeter and 2 centimeters. Then you might have that reflection and translation. You can write it down as E1 plus E0, 2 times by D, where D is the distance of the, let's draw some footsteps here. So that is an example of a transflexion that I've just drawn there. And that transflexion, the transformation that takes this foot to this foot, this foot to this foot, is this transformation, where D is just the distance from sort of there to there, right? Right, so that's D. Okay. So that's where you might see this object But in some sense, this object has another sort of use, which is that but also a reflection. Yes, so that's a reflection. In order to get this, I've taken this foot, and I have reflected it, and I have translated it. So reflect in that line. Oh, do you know what? Let's have it be a different color. Reflect and translate. Right? That reflection and translation is what this object does. All right. E012 is not a reflection. E1 on its own would be a reflection. E1 is the case where d is equal to 0, so that would be reflecting it and then moving it a distance of 0. So that's a transflection in the context of 2D projective geometric algebra. And I'm trying to encapsulate this in... I'm just talking about 2D projective geometric algebra here. 2D projective geometric algebra, by the way, is very, very nice as a way of giving yourself an intuition for 3D geometric algebra, because so many of the principles of 2D projective geometric algebra transfer to 3D projective geometric algebra. All right, so you can take you can E1. So what's the symbol for the? All right, this different people use different notations, I think, but one notation that a lot of people quite like is to have a star. So E12. Let's put a star up here. I think it's actually supposed to go on the left, but I just can't get used to that. I can't get used to that. So this will have to do as our notation for the Hodge dual. E12 star equals E0, because E0 is the thing that's inside of that element there, which is not in this element. It's one way of saying it. Is one way of getting an intuition for it. There's a... You've got it. Okay, one thing that's very important to say. If you are a programmer, the Hodge dual is ridiculously trivial looking. It is just turning an array upside down. Okay, you can add some minus signs. That's it. Turn the array upside... If you've got an array of coefficients for, so an arbitrary object in 2D projective geometric algebra, probably worth writing this out at least once. So A plus... It'll be an array of... yeah. So if you had an array that was like A, B, C, D, E, F, G, H, I, 1, 2, 3, 4, 5, yeah, I didn't need the last one, and this was an array of floats, all right? So just got a simple old, each of these is a float. That could correspond to A, in the mathematical world, that could correspond to A plus BE1 plus CE2 plus DE0 plus... Oh, I gotta get these the right order. Yeah, E12. And apologies that the letter E is appearing in both of these contexts, but just please bear. Okay, tell you what. How about I draw for this one? I'm going to draw the E's here using a nice like that. Okay. Oh, Didn't want that. 1, 2, plus EF, E 1, 2, E 0, 1, plus G, E 0, 2, plus H, E 0, 1, 2, where I have completely forgotten my notation. Okay, plus F plus G plus H. All right. If you're building a game engine on projective geometric algebra, if you're being unoptimized, then you will carry this around everywhere. Actually, it is a little bit better to have arrays of only, what would it be, 4 floats. Yeah, that's generally better. But the thing is that you can just have one. Okay, do you know what? I'm not going to talk about optimization. All I'm just going to say, I'm not going to talk about optimization in this talk. All I'm going to say is, in a mathematical sense, in theory, any object can be a combination of can contain all of these elements. Because you can add all of these together. There's no mathematical law that says that you can't do E1 plus 3 plus E01 plus E012. You could do that, but that's really perverse. It never comes up in a game engine. So one fast way of saying it is that this array always contains at least half of the elements as zeros, and so the obvious optimization, and making it a bit and a simpler way of thinking about it as well, is to take out the objects that have taking out this and this, and you can put those into a rotation. A rotation will only have, it'll only have, well, A, E, F, G. And a translation will also be like that. So a translation will be like that as well. A point will always be a rotation by 180, so it'll always be just a point will always just be E, F, G. And then you can even optimize it further by saying, never mind. So there's rotations and points. And then you additionally say, well, I can also have separately B, C, D, H. Where, look, so I said to you that we've got a transflexion up here. This is a transflexion. It's a reflection followed by a translation along the line that you just reflected in. And that can be represented using this thing down here. See you, man. The Hodge dual for 2D projective geometric algebra. The Hodge dual in general, if you store things this way, then all you're doing is that you're taking A, B, C, D, E, F, G, H, and you're turning it into H, G, F, E, D, C, B, A. And then if you feel like being pedantic, you can put in some minus signs, and those the minus signs. Why are they even there? They don't particularly need to be there. I'm not going to go into that because I don't understand it that well. they're there in order to make it so that things a bit, because this choice of they're there. The minus sign, you can have the minus signs if you want to be really consistent about it being the case that A multiplied by A star equals E012. That is a defining relation for this star thing. It turns out that that is not sufficient on its own to completely define it mathematically, but certainly if you're a software developer, that this is this is all that you're doing. You're just taking some floats and you're taking an array of floats and you're turning the array upside down. That's nice, right? And how on earth could a mathematician engineer resist the temptation? It's not some horrible temptation. It's a really nice thing. It's a really nice thing to take this system here, this beautiful system, which has also projections, new line, orthogonal objects. It's very tempting to take this system and bring in this one extra thing, and be like, look, that lets me get lets you get some formulas that'll measure distances for you and take joins for you. That's what it does. That's the Hodge dual. The thing is, and it's a different. There's at this point a difference of what's going to be interesting to a given person. You know, if you're if you're just a programmer, you want to get strange. If you're a programmer, you might be okay with something like. I mean, I just told you that, there's some, like, fudging over the minus signs here, like this definition being not completely complete. But, like, if you're a programmer, like, this seems like a bloody good definition. It's just that if you're... But this was actually a thing that was a major reason why people didn't adopt projective geometric algebra for many, many years. So, like I say, it was John Selig writing the paper in 2000, and nobody, so far as we know, Charles Gunn was the only person who picked it up in 2005. John Selig was part of the geometric algebra community, and something that's probably worth mentioning is, at this stage, okay, so I can make some sense of what happened now. John wrote that. John had the idea, and he was in the community of people applying geometric algebra and applying spinors and just abstract algebra generally to applied mathematics and physics, at that time the community wasn't ready for the ideas, I guess you have to say. Partly because conformal geometric algebra was just getting big, so lots of people were starting to use that, and projective geometric algebra is strictly a subset of conformal geometric algebra. So a lot of people were like, I'm going to learn conformal geometric algebra anyway, so I'll just focus on doing that, and not bother with this projective geometric algebra thing. Leo Dorst was aware, I understand, of John's work, and he wrote so Leo Dorst is the author of a book called Geometric Algebra for Computer Scientists, and there's a chapter in that book that's called Geometric Algebra and Homogeneous Coordinates, or something like this, and the Homogeneous Model. And nowadays, Leo views projective geometric algebra... Well, he's rewriting his book to use it more, and he's certainly rewriting... That chapter has already been rewritten. So if you've got an old copy of that book, then it's very much out of date in everybody's opinion. But it was through that book that Eric Lengyel realized what how much amazing stuff could be done with realized projective geometric algebra independently of Charles. And John isn't cited in the first edition of Geometric Algebra for Computer Scientists. And Leo would say, he was part of the one of the people who was not really ready for John's ideas. But you got to consider that in some sense Selig influenced that paper, or that chapter of the book. Anyway, a thing that's probably also worth mentioning as a side note, by the way, there's something else called the Poincaré dual, which I won't go into, but is another part of the debate that was happening at that time and has continued. So there are some folks who use, so here at Cambridge, so Anthony Lazenby and Chris Duran to some extent, Anthony Lazenby and Joan Lazenby certainly, they use something else called the Poincaré dual. So sorry if you thought it wasn't already complicated enough. But I think they're rather unique in doing that, and I don't personally see that catching on. And the Poincaré dual is something which, again, allows you to do this little arrow here. So this arrow down here that lets you escape from the confines of this algebra and get into the broader thing. There's just multiple ways of doing it. And the Hodge dual is in some sense the simplest. It quote unquote allows you to ignore polar geometry. But the thing is that from some people's point of view, that's a really sad thing. You're letting yourself down. You are not letting yourself in on potential connections to camera zollies. So that would be something that I'd say is nice about it. But I have to admit that, I wouldn't say that that's worth it, and certainly not if you're a beginner. Forget about it. The reason I'm doing this lecture is because I really want to clarify why there became this notational difference, and that's part of the answer to this question. But I personally don't see the case for beginners learning polar geometry, whereas Euclidean geometry is the thing that we teach in school. We teach you we teach you that the angles of a triangle add up to 180 degrees. And we teach you about distances and angles, and you're generally expected to believe that if you have 2 points and you measure their distance, and then you move both of them, you subject both of them to the same transformation, and then you measure their distance after having done that, you'll get the same answer as when you started out. That's not true in hyperbolic or spherical or polar geometry. Or for that matter, the really weird ones like solve geometry or nil geometry, or there's another. There's other weird. There's all sorts of strange kinds of geometry, but Euclidean geometry is really important. Euclidean projective geometric algebra is a brilliant way of doing Euclidean geometry. Lets you do rotations, translations, points, lines, planes, all this stuff very, very well. And then polar geometry is academically interesting, but not that useful for an engineer. Which is why I wouldn't say, if I was in charge of an undergraduate math syllabus, I'd teach this and I'd teach the Hodge dual. I would not teach the projective dual. But of course, you know, if you're a master's level mathematician, of course you should know about it. Yeah. So what happened? Let me say a bit about the notation. So I've given a probably an accurate idea of what the Hodge dual looks like. But just to say, when you read the work of Stephen de Koninck and he says dual, that's what he's talking about. He's talking about the Hodge dual. Which is this, you know, again, this turn the array upside down thing. The Charles Gunn thing. So Charles, when he was discovering this stuff, he said he adopted the following notation. Yeah, let's just be pretty blank slate. Charles says R301, and that R with a big R like that, and I think that can also be written as R301. Sorry, he has that, and he has R301 star, and that's an asterisk we've got in there, not a pentagram. I think Stephen uses a asterisk for the Hodge dual in general, but yeah, okay. And you can also write that as this 301. Right. His reasons for doing this are his one reason that you might do this is because people are taught about R3, right? Yeah, they're taught about R3, and basically, I don't know, I guess personally I would say that people end up, whether or not it's taught well, people end up with the understanding that R3 means Euclidean space. But this is not strictly true. R3 is an algebra. R3 just means yeah, correct. Sorry. So the Ganja, to take the Hodge dual in Ganja is a exclamation mark followed by the element. But yeah. Okay, so there's R3, and R3 the reason that people make this connection is because you can add together, you can concatenate arrows, and that does Euclidean transformations. If you do Euclidean transformations, that does Euclidean translations. Euclidean transformations is a broader term encompassing rotations. But as we all know, if you've got to do a rotation, you tend to use a different bunch of maths. You don't do just okay. You can kind of do rotations if you use the Rodriguez rotation formula, but the real history is that there's this thing called a Gibbs vector, and a Gibbs vector is a thing that goes into and comes out of the cross product. But the thing is that, let me write down the thing that's actually true. Like, R3 can model Euclidean it can model hyperbolic, it can model elliptic. And when I say that, I mean elliptic, three-dimensional elliptic space. So not just the surface of a sphere like this, but like a weird, if your universe was such that if you go far enough in that direction, you come back in this direction. That kind of three-dimensional universe. You can use R3 to model all of these. You kind of just got to understand the metric with respect to which you are normalizing, and okay, you can assume that's the Euclidean that's Euclidean space, but that's not. Well, anyway, so that would be a rant from that would be that's a clarification that Charles is careful to make. Whether it's Euclidean or not comes from how you normalize the objects that you're working with. All right. And so he has this one to mean... he has this one to mean... Euclidean projective geometric algebra. Wow, that's tiny. Let's just say Euclidean PGA, and then this one is polar. Well, what I'm calling PGA. Charles calls it dual Euclidean PGA. Wait. Yes, he does. But the star goes down here because another word for this that you might have heard is point-based PGA. And then this is plane-based PGA. Right, that's plane-based PGA, and that's point-based PGA. Many people have tried to make it so that you can have PGA. So Chris Duran, John Selig originally tried to make. They tried to do Euclidean geometry in a situation where you had points as grade 1 objects. It doesn't work. The maths does not work. So the maths does not work. That's an important part of the story. So that's what trying that led. So Charles Gunn also tried to do Euclidean PGA in a point-based way, and was led to the John Selig way of doing things. Was led to John Selig's paper. John Selig had the same thing going on. Eric also was in the same way, but the thing is that it turns out, when I started out with projective geometric algebra, I got the impression that there was the point-based school and there was the plane-based school, and maybe there was also conformal geometric algebra as well. The plane-based school was Stephen, and the point-based Stephen and Charles, and the point-based school was Eric. But that's not exactly true. That's never been true. So what there is there's the plane-based plus Hodge dual school, and that's Stephen and John Selig. And there is the both school. There is the use point-based and plane-based school. The school of use point-based and plane-based projective geometric algebra. And well, I say the school, again, there was the notational differences, and so Eric and Charles, their stuff doesn't seem that compatible, especially because the main way that Charles's stuff reached reached a broader audience was via Stephen, who put aside point-based PGA and polar space. But yeah, that's what happened. That is what happened. So, Charles. So there's a very natural thing that you can do. I don't know who started doing this. I don't think it was John Selig. But there's this notational. I'm getting into the notational and conceptual differences now. The notation, I kind of started us off by saying the notation looks like this. So you've got, do you know what? It's time to start again. You've got A, B, and that's the geometric product. Yeah, okay, and wedge product, A, wedge, B, inner product, A dot, B, regressive product, A, V, it's called the V symbol, B. All right. I've tried to strain this. These are notations and words that people use for algebraic operations that they define, but they can define them in different ways, is the thing. And different people have different ways of defining them. They have different ways of introducing you to their definitions of them. They have different opinions about what should be fundamental and what should not be fundamental, and that leads to potentially so many differences that even if there's the same maths going on underneath, it can be very hard to see that. All you can do is try to clear up the differences when you see them, or maybe try to learn both ways of doing it, and then see that this one can do this, that one can do that. But ideally things would be easier for newcomers. There wouldn't be different ways of doing things, but that's the way it's going to be. So I've written down the algebra. The algebra, I've written down the notation. Okay. Notation. And then geometric interpretation. And that's a different thing. Transform composition. Which is which if you're in it, do you know what? Let's not have that one. Composition of Euclidean transformations. With a little S on the end there. If you've got a rotation and another rotation, well, the geometric product can give you this rotation followed by that rotation. Intersection. Element that is orthogonal to A and passes through B. No, let's not have that. Element that is orthogonal to A, new line, and passes through B. regressive product is join. No. Join. Those are some geometric interpretations you can give. And one reason that you tend to, that you can notice that, like, this here is this, but upside down, right? And that's because there's this kind of pleasing, symmetry, we say, where intersecting two things is a little bit like joining two things. It's a little bit like joining two things, right? You take and in fact, in that with that duality thing that I was talking about, that gives a precise, satisfying mathematical correspondence between these two different things, which you very frequently want to do. And then taking distances and taking angles is basically, you've got the same sort of thing going on. And so you can see why you want to have this going on. You can see why you want to have, some connection between the two of them, and some idea that one is the other, but with a flip, with some kind of flip applied to it, where it's a flip that if you do the flip twice, you get back to where you started. There's a word for that mathematicians care about a lot, but I can't remember what it's called. So that's a very appealing bit of typography. A and B are linear primitives. Yes, A and B. A and B. If you're doing, A and B are points, lines, or planes. All right. A and B are points, lines, or planes. If A and B are a plane and a line, then their intersection is the point where the line meets the plane. Correct. They're also linear transformations. If A is a reflection, then it's a reflection in a certain plane. If A is a line, then it's a 180-degree rotation around that line, aka a line reflection. If it's a point, if A is a point, then it's a thing that takes that point and you start out here and you end up over here. That's what they are. Both A and B are shapes, and they are also transformations that preserve those shapes. Certainly, but the question that you can ask is, hey, are they those objects in Euclidean space, or are they those objects in polar space? And those operators are uncontroversial projective operators. I don't think I know exactly what you mean by projective operators, but these I have not. What's going to happen is that these operators get used by Charles Gunn and Eric Lengyel in different ways. So what happens is that if I draw a picture of, I'm going to draw two pictures. I can't remember the color scheme that I used before, so I'll just pretend. Dark blue for Euclidean space, and Euclidean space. These are things that you find in Euclidean space, reflections, and points. 2D Euclidean space, 2D polar space. You also find, you know, lines and points in 2D polar space, but the kinds of you don't really find reflections, for example. You find weird sort of things that'll like they'll do a reflection, but it'll look like sort of like this, or it'll be a rotation, but it's a rotation that kind of preserves a line instead of a point. I don't know it very well, in spite of having made polar Tetris. But 2D polar space, the thing is, the key conceptual difference between Eric and Charles, and I think I can say this as one of the few people on the planet Earth who understands both of their work well enough to take a position on it. The key conceptual difference between Eric and Charles is that Eric really likes to say that simultaneously there is a... Do you know what? How about we... Simultaneously, if you have a line in here and a point in here, it is that at the literal same time. At the literal same time. So if you write E1 plus E0, for example, that can be literally this and this at the same time, whereas Charles has he's really close to feeling the same way, but Charles would prefer to say that this is an object separate to this that is related by a... Oh god, I guess I gotta use a different color. Eric, Charles, both... An algebraic element corresponds to an element in point... An algebraic element corresponds to an element of polar space and Euclidean space at the same time. An algebraic element corresponds to either an element in polar space or in Euclidean space, new line, and you go between them using the dual operator. And that is the main difference, I would say. Right. Charles, I just want to clarify, Charles is really close to thinking something like this as well. But, I don't know. At this point, the main conceptual difference. That's it. And Eric wanted to have a notation that did this one, and Charles wanted to have a notation that did this one. All right. I haven't had a notation. Yeah. I don't know. So Charles has written a paper recently called Variants of Duality in Projective Geometric Algebra, and he advocates in that paper having E1 and E1. So this could correspond to... But that's exactly the kind of thing that Charles would do, but that Eric might not do. Eric might do it the other way around. And one thing that happened was that you can get the impression that Eric really strongly Eric, I think it's safe to say he somewhat prefers thinking about things in a point-based way. If you think about things in a point-based way, bear in mind that... we've got a question. So, are polar spaces and Euclidean spaces both models of the theory defined by the operators? Other way around. The operators are trying to... encompass things going on in polar space and Euclidean space. Yeah. I think it's safe to say Eric somewhat prefers being point-based. But because he's got this thing like, oh, you can, because it's literally both at the same time, because E1, for example, there's a single thing called a single thing? Yeah, there is a single algebraic object called E1, and that corresponds to objects in, an object in 2D Euclidean space and an object in 2D polar space simultaneously. And because he's got that going on, he's like, well, it doesn't really matter which one you prefer. You could prefer the other thing, and you'd get really similar results. One reason that, and then, right, need to say, to go back to here, in Euclidean projective geometric algebra, let's make that a bit more consistent. Why didn't it have the last 3 letters? That's weird. Okay. We're going to have another one of these. You have composition of polar space transformations. All right. Geometric interpretation in polar projective geometric algebra. And they've got a different thing. And yeah. Right. I've made sort of I've sort of made a mistake here, because, yep, I've made a mistake here with editing that I was doing. So the join doesn't exist in Euclidean projective geometric algebra. The join does not exist. The join is something which you have to extend yourself to projective geometric algebra. You've got to use the dual. It's really simple looking, by the way. I should write it down. Like A wedge B again does yeah, I can use what I wrote here. A wedge B is equals the point. If you know, yeah, you get which one is A and which one is B. If this is A join, right? A join B is the line, and one way of rewriting this, in some sense, is A star wedge, yeah, wedge B, wedge B star, whole thing star. Yeah. It turns out that is all you need to define the join. And the join is very useful. And the join, and so in some sense, we've just spent the last God knows how much time. How long has this been going on? I don't even know. I don't want to know, I don't think. We've spent the last, however, God knows how long, defining this frickin'... looking at the geometric interpretation for this frickin' formula. I mean, I've just used the Hodge dual there. I haven't given a symbol for the projective dual, but the point is that if you were to say that that star symbol corresponded to the projective dual, then this would still work. And you've still managed to define the join in terms of the meet. Now, to be clear, I've been using Charles Gunn / John Selig's notation here. Because remember, yeah, okay, so the way that it works is that this guy and this guy, conceptual similarity, new line, notational difference. And then this guy and this guy, well, no, how about these guys together, so everyone except for Eric, have a notation, unified notation. I should have done that with a different color. Let me do that with a different color. Yeah. Notational unity. I'm hesitating to put conceptual similarity there. Yeah, okay. Because there is not conceptual similarity between Stephen and Charles. There is. I don't even feel like there's conceptual similarity between Stephen and John, actually. Although I would say that they are conceptually more similar to one another than Charles and Eric are to one another. And then Leo is working on his own thing as well. But the point is that the conceptualization is really similar between Charles and Eric, but the notation is extremely different. And then the notation is very similar between... is identical between... Well, no, I shouldn't say identical. The notation is very similar between Stephen and John, but the notation is very... Ugh, I should have just done this. Yes. Okay, this is the right way of doing it. Because these are the people who are sort of most important to the story of how things became... how people became aware of things. Conceptual difference, new line, notational similarity. That's what happened. That is what happened. Right. And this uses the John Selig, Charles Gunn, Stephen DeKennick notation. Oh, yeah, that's true. That's the John Selig, Charles Gunn, Stephen DeKennick notation. But part of the note, I'll draw a very okay. So we've got questions. So in Euclidean projective geometry, we have the geometric product, wedge product, and inner product. Yes. And then in projective geometric algebra, which is broader than Euclidean projective geometric algebra, we have the geometric product, the wedge product, the inner product, and the Hodge and the dual, which could be the Hodge dual or it could be the projective dual. But the point is that allows you to define the regressive product. The regressive product does joining of elements. All right. There was a moment where everyone's notation could have been the same, because Charles and Eric both faced... Oh, okay. regressive product is where all the controversy comes in. Yeah, the wanting to join elements and wanting to take distances between things. Euclidean projective geometric algebra on its own can do composition of Euclidean transformations. It can do intersections. It can do orthogonal objects. It can do projections. It can measure angles, but on its own, it cannot measure distances, and it cannot take joins. So it can't join a point and a point to get a line. You have to step outside of it. You have to use the dual in order to, get that. And the controversy is over the different notations and conceptualizations of the dual. Right. There was a moment where things could have been... Thanks, Alex. I'm glad that you get... Yeah, goodness me. This is quite a ride. I mean... Yeah. Quite a ride. So I need to finish off saying how the notational difference came about, because, you know, Eric's notation is quite clever in terms of doing what Eric wants to do. I mean, one thing that I may or may not have time to go into is that Eric was entranced by a seeming connection between this particular part of projective geometric algebra and the De Morgan laws, which are a concept in logic, so Boolean logic. And the De Morgan laws are a very fundamental aspect of, logic, I suppose. And, you know, that it almost suggests a kind of metaphysical connection between logic and geometry to have something analogous to logic in there. And, you know, you can see why somebody would be very interested in that metaphysics there. I mean, maybe there's even other people who have, other than Eric, who have gotten interested in that. But anyway, should finish off saying this. So, the place that we're going to is that you've got Eric decided that this notation for the geometric product was not going to cut it. So, and the nice thing to do would be to have a product like this and a product like this. That's what Eric wanted to have, and that made sense in context. So this, just talk just a little bit about the typography of this. So this symbol is, I think, part of the it's something like it's part of the extended Unicode standard, and it and Eric is a sponsor for the pair of these symbols in it being accepted into a Unicode standard on all browsers or something like this. So, and the reason that it's kind of clever to have this is because you can write the following equation. The following equation is going to be accurate for, let's say, quite a lot of maths, all right? So a dot b plus a wedge b equals ab. That's a definition for the geometric product. That's the first definition that William Clifford wrote down. And that's why we call it I think we call it the Clifford product sometimes. But anyway, so that's a dot b plus a wedge b is equal to the geometric product of b, except actually this isn't quite true. This is not quite true. If a and b, for an example of this in projective geometric algebra would be the case where a and b are both lines in three-dimensional space. So maybe try to draw a cube for them, just to remind you that these are three-dimensional lines. These are three-dimensional lines. These are lines in three-dimensional space. And if you have a transformation that is a 180-degree turn followed around line A, followed by a 180-degree turn around line B, so you're composing the transformation A and the transformation B, that'll get you, in general, a screw motion. It'll get you a screw motion, and it will have a part of that object that you've gotten by taking the product of A and B will be part of that part will be the inner product of A and B. Part of it will be the wedge product of A and B, but there'll be another part which will not be equal, which will not be contained inside of the either the inner product or the wedge product. So this only true in a limited set of contexts. I think that my listener is sort of cutting out early. Yeah, but that being said, it's true for quite a lot of contexts. So, for example, if A and B are both they're both planes in Euclidean space, then this is true. This equation is true, and that's pretty useful. And because we turn the wedge product upside down to get the regressive product, we take or to put it another way, intersection dualizes to joining, or the meet dualizes to the join. Because we do that, Eric was like, well, this seems like a pretty nice thing to do. And so he got interested in the question of what does this thing mean? Because, I guess John Selig had at least defined this, and certainly Charles Gunn had defined it, though Eric wasn't aware of that. John Selig had defined this, but nobody had defined this before. So what would this be? Well, what would this be? This, to do this, is to take the, well, yeah, I can write it down. A star, B star, whole thing, star. That's a pretty sensible thing to do. And you've done it in order to get the intersection, well, to get the join. Depending on... okay. You've done this to get the intersection, to find a relationship between the intersection and the join. So this, this is the definition of this, which is the geometric anti-product, or the anti-geometric product. And that is a product which only Eric uses. And other people who have been interested in Eric's work. There's some places where you can kind of make the case for it. There's not that many situations where you can say that there's not that many situations that I'm aware of where you really you can do something with it that you can't do with the geometric product. Although, with that being said, that what I just said sort of also applies to the wedge product. Anyway, that gets into the conceptual differences. The anti-geometric product, plausibly, whereas the geometric product does composition of Euclidean transformations, the anti-geometric product, you could potentially use it for thinking about compositions of transformations in polar projective geometric algebra. Plausibly. But there's lots of things which you can do with the geometric anti-product, which Eric would use the anti-geometric product to do them. Stephen, for example, or John Selig would use the geometric product, or the inner product, or whatever. So yeah, there ended up being not only a difference of conceptualization and notation, but also a difference of suggestion of which one you should do. So to give an example, like if you've got 2 points at infinity, and you want to get the rotation around a line specifically through the origin that takes you from this point to this point, that would take you from facing towards this point to facing towards that point. Well, if you were Stephen, you would take the duals of those 2 points, which were the Hodge duals of those 2 points, which would get you a pair of planes that pass through the origin, and then you take the geometric product of those planes. Whereas if you're Eric, you could take their geometric anti-product. I think that would get you a rotation in polar projective in polar space rather than in Euclidean space. Whereas you're a bit more likely to want one in Euclidean space, but there it is. And if you want to know the angle, that if you maybe don't want the transformation, but you just want the angle that you'd move through to get from here to here, well, if you were Stephen, again, you would dualize and you'd take the inner product of these 2 planes. Whereas if you're Eric, then you would take the inner product. I've screwed myself up, so apologies to Eric again. You wouldn't take the inner you would take the inner product. You'd take the inner product of those 2 points, but I'm getting into the sad thing that happened. So, Eric, having decided to have these 2 products, faces an arbitrary binary choice about which one should mean which. All right? So, Eric has these terms. Eric, anti-geometric product, new line, anti-inner product, and new line, anti-wedge product. That and worked out well for me. Those are terms which he uses. Anti-reverse, new line, anti something. There's a few. I think there's anti projection, and these are all terms which appear in his notation but not in others. And he uses them a lot because here was the thing: he had to decide which one was going. He calls one of them space and one of them anti-space. Oh, and he's got the term vectors and anti-vectors, bivectors and anti-bivectors, and he faced an arbitrary choice about which one he should call space and which one he should call anti-space. And he chose the one that he chose to do it the way around that made him incompatible with Charles's way of doing it. Dang, as Hella Hex says in the chat. If it was an arbitrary choice, like Benjamin Franklin, he had to choose one, and he chose the one that made it harder to integrate his work into other people's work. But he also chose the one that made it so that he mostly works in a way conceptualizes. His conceptualization of a vector is that it is both simultaneously a point and a plane. It's but his he tends to think about vectors being points, which is something that Charles can be done in Charles Gunn's way of thinking about things. It's just that Charles Gunn would be thinking about polar space when thinking about that. And yeah, I think you get the picture. Well, what happened was that gave the impression that Eric was thinking about point-based projective geometric algebra, whereas Stephen was thinking about plane-based geometric algebra. And that statement that I just made is kind of true, but not really. Not really. See the previous... Again, see what I've just said. Yeah, they got that impression. And, yeah, that made it hard. You know, their notation doesn't look at all similar. So even though at least Eric and Charles are looking at similar things, and there's so much overlap. I mean, Eric talks about the Hodge dual as well. Yeah, what are you gonna do? You know, the future is bright, I would say, because you know, again, we're looking at a way of grounding them both in conformal geometric algebra, which is also something that I don't know if a first year undergrad engineer needs to know about. But I would say that a first year engineering undergrad should learn Euclidean projective geometric algebra. And then I would teach them the Hodge. Well, and I'd teach them the distance and join formulae. This is what happened in my GDC lecture. I gave a presentation without actually mentioning the dual. I do use the dual implicitly when I'm taking the distances of things. But this is the thing. You only need the dual to do essentially two things. Number one, measure distances between things. And number two, take joins of things. And, you know, it's so sad that that in some sense a relatively small thing could lead to so much confusion. You know, this plus the previous slide. But yeah, so, you know, to fill in this, the wedge product. Yeah, the wedge product. So in some contexts, the wedge product can mean the join rather than the meet, and then implicitly the V product would mean the meet if you were doing things that way around, and that can happen in the work of both Eric and Charles, but the opposite way around, always. I think that might be it. So there you go. Please put any questions in the chat. I'm just going to check that I've said everything that I wanted to say. But if you have any questions about this whole thing, then I'm happy to answer them. Oh, no worries, Dugan. One thing that I guess I want to say is that there's this word vector. Yeah, this will. Oh, we've got. Yeah, I guess there are no questions, so this will be the last point. And I'm definitely gonna come back multiple times to what I'm just about to say, but I'm going to say just one last thing about the word vector. I'm going to make it big as well. It's a big old important word. What is a vector? Well, a vector is the first thing that you learn about when you go to university to study engineering. And it's a thing that we use in video game graphics, and it's a thing that we use in machine learning and in all sorts of places. There are I would say 2, really 3 definitions of the word vector. Definition 1. No. Okay. Definition, new line, definition, new line, definition. Ah, damn it, didn't work. Thought I got it. Definition, new line, definition, new line, definition. Okay. A thing that goes into and comes out of the cross product. Yeah. Definition 2. A grade 1 element of a Clifford algebra. And definition number 3. A thing that you can add and multiply by scalars. We've got a question. Do I ever need to care about the difference between dual and undual when working with PGA and CGA? Good question. Engineering-wise, no. Nope. In a research context, maybe. Because I think with some of it, it's the case that if you dual and that, I'm not exactly the right person to ask, apparently. But in general, no. Like the dual, it's okay to be sloppy about it, honestly. That's why I was being so hand-wavy about the minus signs. For a long time, my code didn't have the minus signs in it, and the bivector.net generator for projective geometric algebra didn't have the minus signs in it. Never mattered, because the minus signs, because the dual, you tend to only do it. Again, you're only using it for the join and the taking the distances of things. And with the join, you tend to write that code out. Ugh. Anyway, yeah, doesn't matter. The only way that a minus sign can change things is potentially making a rotation go this way instead of that way, in which case you can just multiply the bivector part by -1. Yeah. Okay. It's spelt the word scalar wrong, but yeah. So those are the 3 definitions of a vector. And the historical development was, oh god, I know that, well, this is the one that's this definition of a vector is, in my opinion, well, okay, in my opinion, it's the best one. I'm allowed to say that. The nice thing about this definition is that it's completely unambiguous. You're not saying anything more. And this definition also applies to these definitions, because you can add and multiply scalars by things that go into and come out of the cross product. And you can add and multiply by scalars grade 1 elements of a Clifford algebra. But the thing that people don't like about this definition is that it's so vague. It's very, very broad. So if you go by this definition, the phrase "the vector part of a quaternion" makes no sense, because the whole quaternion is a vector. This definition only makes sense if you like the cross product. Definition 1 only makes sense if you like the cross product. And then here's people say people say this, use this definition as well, and I hate that. I desperately wish that we could just stop people from saying, like, I wish a bolt of lightning would strike anybody who says the word vector when they mean grade 1 element of a Clifford algebra. Here's why. The whole of a Clifford algebra, including the bivectors and the scalars, are also vectors by definition 3. And so you have this word bivector, and a bivector means a grade 2 element of a Clifford algebra, and then a trivector is a grade 3 element of a Clifford algebra. So a grade 1 element, you should call it a univector, but nobody wants to do that. They're like, oh, it's fine, everybody knows what I mean. So they just say they just say vector to mean grade 1 element of a Clifford algebra. And, you know, I'm not the kind of guy to sit and pretend that I don't know what they mean, so I go along with that definition for the purposes of the conversation, because I'm a linguistic descriptivist, not a linguistic prescriptivist. But, you know, well, I'm being a bit linguistic prescriptivist here, aren't I? The picture of a vector that people draw looks like this. So if, like, I don't know. Right, so there's there's our axes, x, y, z, and that's a vector. And that's what you get told is a vector. Well, a vector is a much more broad thing. A vector, the best definition of a vector is this, and so a vector is anything that you can add and you can multiply by scalars, all right? A vector is that. So, you know, if you want to make a sandwich, is a vector in the space of sandwiches, all right? So, and you wouldn't necessarily say, yeah, a vector as an element of a vector space, right? You wouldn't say, I'm going to the kitchen to make myself a vector. You'd say, I'm going to the kitchen to make myself a sandwich. So it makes sense to be a bit more specific. If you want to be a bit insufferable, then you actually call this one you call that a Gibbs vector. Good, it knows the term Gibbs vector, because Gibbs was the person who looked at the quaternion product and said, I don't like it being this way, I'm going to separate this out into two separate things. And that part kind of makes sense because they are separate. There's the scalar part and there's the bivector part. But then he was like, I want to think about moving in a direction in the same sort of way that I think about rotating around an axis. So, because a vector is something that you rotate around, you can have the vector part of a quaternion, even though it's a bivector, even though a bivector is a vector by definition number 3. Right? It's horrible. And because you're taught to think about everything as vectors, by which you mean arrows, because you're taught to think about everything as vectors, so like, you know, a point is a vector, and a translation is a vector, and a direction is a vector, and a rotation is a rotation around a vector. So this becomes the hammer for which everything looks like a nail, even though a direction and a point in three-dimensional space, a point in space, and a translation and a rotation axis, those are all different frickin' kinds of thing, and in projective geometric algebra you get them as different kinds of things, thank you very much, which makes it better. But a Gibbs vector tries to be, at the very least, a translation and a rotation at the same time. And so when people say that Stephen Decanic believes planes should be vectors whereas Eric Lengyel believes points should be vectors, that statement contains a grain of truth, but it's so grotesquely confused by this stuff. And have I still got it? Well, yeah, by all of that stuff. That's what it takes to interpret the phrase Eric Lengyel believes points are vectors, and whereas Stephen Decanic believes planes are vectors. Don't try and take that phrase on its own as a description of what the difference is. Yeah, I'm afraid that's the way it is. History, it's complicated. So I better get going. Thank you everyone very much for coming. Who knows, maybe I've gotten some aspects of it horribly wrong, and I'll need to be corrected, and I will correct it, because all of these people owe it. I owe it to all of these people to get right their beliefs about things. But yeah, I think that's the best summary of it that I can do. So I hope you all have a nice week. Send me along any questions that you have about this. Hamish_Todd on Twitter. See you all 5 p.m. again